types of covalent bonds, polar and non-polar bonds. Then bond parameters explained. Then after bond parameters, your dipole moment started. And dipole moment definition as well as formula, percentage of ionic character explained. Now in dipole moment, one important concept is applications of dipole moment. Generally in examination, based on applications they'll create, which of the following molecule shows polarity, certain polarity, or molecules are symmetric or unsymmetric, or which molecule is more stable on the basis of dipole moment. Such questions arises in objective concept. Okay, so here based on dipole moment, one important concept is applications. Applications of mu dipole moment. Okay, so in this applications of dipole moment, first I'll give the dipole moment mu is directly proportional to electronegativity and also directly proportional to lone pair of electrons, and it is inversely proportional to angle between two atoms which are bonded at certain. Now this moment, dipole moment, is directly proportional to electronegativity. Means, for example, here for this point, are the hydrogen fluoride, hydrogen chloride, HBr, hydrogen bromide, and HI. Once we can observe these four examples, fluorine, chlorine, bromine, iodine, among these highest electronegativity element is fluorine. Now the dipole moment is generally denoted by a symbol like hydrogen to fluorine. Moment is from electropositive to electronegative by an arrow. On arrow there is one cross line on tail. This is the symbol of dipole moment. It is from electropositive to electronegative, partial positive and partial negative charge. So the dipole moment is mu is the product of a charge into distance between the two poles. How to calculate the distance explained. Now for these units are dBA. Here 1 dBA is equals to 3.33 into 10 to the power minus 30 coulomb meter, that is equals to 1 into 10 power minus 18 ESCU centimeter, electrostatic units, ESU means. Now this is in SI system, this is in CGS system. It is in vector quantity because it depends on both direction and magnitude. Definition explained and units explained in last class. So once we can observe between hydrogen and fluorine, there is electronegativity difference is there. Your electronegativity difference is more, dipole moment is more. Its charge and distance value also increases. Okay, that's why based on this point, based on electronegativity, hydrogen fluoride is more has more dipole moment than compared to the hydrogen chloride, than compared to hydrogen bromide, than compared to the hydrogen iodide. This is first example. This is. Now second one is dipole moment is directly proportional to LP electrons, number of lone pair of electrons. Once we can observe here H2O water molecule, NH3 ammonia molecule, and CH4. This is methane. Your central atom of element is oxygen. It contains two lone pair. Two lone pair. Now its value is its dipole moment as certain dipole moment. Now central atom of an element in ammonia is nitrogen. It contains one lone pair. Now here the three hydrogen atoms are bonded. Now in CH4 there is no lone pairs tetrahedrally arranged like hydrogen, 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 and hydrogen. So based on this, dipole moment is more when number of lone pairs are more. Lone pairs increases, bond dipole moment also increases. See here two lone pairs are there. These two are the lone pair. This is lone pair 1. So compared to this ammonia has less dipole moment. That's why in water molecule dipole moment is more than compared to the ammonia. And ammonia has more dipole moment than compared to the methane molecule. Generally methane is tetrahedral, that is symmetrical. Its dipole moment is equals to 0. But these are not equal to 0. These are not equal to 0. Something value is there. They are experimentally determined value. So among this, which one has a higher dipole moment means this. Without knowing values also, by using this concept, easy to estimate its dipole moment, higher or the lower dipole moment. And dipole moment is inversely proportional to the angle. Means dipole moment is more, bond angle is less, inversely proportional. Say dipole moment is more, but your bond angle is 105 degrees. But here dipole moment is here 107 degrees. Sorry, your bond angle. Your bond angle is 109 degrees 28 minutes. Bond angle is less, dipole moment is more. So here the bond angle is less, dipole moment is more. That's why water molecule dipole moment is more because bond angle is less, and here it contains number of lone pairs, two lone pairs. So how to calculate its dipole moment? If they'll give the angle, one formula is there. Resultant dipole moment mu is equals to square root of mu1 square plus mu2 square plus 2 mu1 mu2 into cos theta. Theta value angle they will do. So by using resultant dipole moment experimentally we can calculate. So based on this, in last class given about dipole moment is directly proportional to electronegativity, directly proportional to number of lone pairs, and inversely proportional to its angle. In this manner we can estimate. Its applications, first application is we can estimate, we can calculate the shape of the molecule. Shape of the molecule, first one. Second one is polarity of the molecule. Is it polar or non-polar? Polarity of the molecule. And also is to distinguish between symmetry and unsymmetrical molecule. Symmetry and unsymmetrical nature, to distinguish symmetry and unsymmetrical nature of this molecule. Sorry, the shape of the molecule means based on their dipole moment. Generally, general point, those molecules are generally having a linear, normal linear shape, and here tetrahedral shape, generally having dipole moment mu is equals to 0, even though having certain moments. For example, here carbon dioxide is there, CO2 is there, carbon dioxide. Its geometry is, for example, here C double bond O and here double bond O. Yeah, compared to carbon and oxygen, more electronegativity is oxygen. Now moment is shown by an arrow. On arrow tail of the arrow there is a cross line, that is from carbon to oxygen, because oxygen is more electronegative. Now here also carbon and oxygen. From carbon to oxygen one moment is there, this is mu1, and carbon to oxygen another moment is there, mu2. But dipole moment depends on means it is vector quantity, depends on both magnitude and direction. In this molecule, this carbon to oxygen certain moment is there, that is considered as a x. Now here the carbon to oxygen also a x here, but is a minus x. Why it is a minus x? Equal, but they are in opposite direction. So in this carbon dioxide molecule, from carbon to oxygen, moment is, if it is x dB, but here minus x dB, because the moment is means dipole moment is equal and opposite in direction. So such molecule dipole moment resultant mu r is equals to mu1 plus mu2. Now that is x minus x, that is get cancelled, that is equals to 0. Such a linear molecule dipole moment is 0, that is the shape of the molecule is to estimate by using dipole moment. So molecules having dipole moment is 0, they are generally linear, tetrahedral, or some cases trigonal planar geometry. For example, boron trifluoride is there, boron trifluoride. In this boron trifluoride, your dipole moment is equals to 0. Because in boron trifluoride molecule, central atom of an element is boron. Around boron now, 3 fluorine atoms are bonded. This is boron. They are fluorine, fluorine, and fluorine. Among this boron and fluorine, more electronegativity element is fluorine. From boron to fluorine, there is a moment, certain moment is there. This is the dipole moment. And also from boron to the fluorine, there is a moment is there, dipole moment. So connecting these two, net resultant dipole moment mu r is equals to 0, because they are equivalent opposite in direction. This is in this direction, this is in this direction. If it is minus x, it is plus x. Resultant is 0. Same similarly, if you can take a third one, there is a moment. Third one, if you can take also boron to the fluorine, comparing these two resultant is 0, comparing these two resultant is 0, comparing these two resultant is 0. Total resultant dipole moment is equals to 0, but its geometry is planar geometry, that is trigonal planar geometry. So those molecule having trigonal planar geometry are tetrahedral or linear. In such cases, the dipole moment must be equal to 0. There is no moment. Even though it is a moment is there, get cancelled each other. So in CH4 molecule, like due to the symmetry, CH4, CH4, and CH4, symmetry, hydrogen to the carbon, hydrogen to the carbon, hydrogen to the carbon, hydrogen to the carbon, equal and the same direction, but net resultant similar structure is there, symmetric in molecule. That's why its molecular moment is 0. Not only in these SiH4, the SiCl4 or CCl4, such molecule, tetrahedral geometry. Even though tetrahedral geometry, there is a moment cancel to each other, its resultant dipole moment must be equal to 0. So here polarity means, polarity of the molecule means moment is 0, there is no polarity, there is no charges. And here the shape of the molecule means based on the shape, here the linear, tetrahedral, and trigonal planar, its geometry, shape of the molecule, maximum in this shape, dipole moment is 0. And also based on number of lone pairs, its dipole moment also changes. I'll give a simple example to you. That is a simple important example is your NH3 and NF3. This is, ammonia and nitrogen trifluoride. In both the cases, central atom of element is nitrogen containing 1,1 lone pair. Now here the nitrogen one lone pair and it is bonded with 3 hydrogen atoms like this. Now movement is from hydrogen to the nitrogen, there is a movement. All are in same direction. All are in same direction. And also here compared to the nitrogen electronegativity, 2 electrons electronegativity is more. That's why nitrogen to the lone pair of electrons. Total all are in the same direction only. There is a moment. That's why dipole moment are not equal to 0. In this case, your nitrogen and there is one a lone pair and your 3 fluorine atoms are bonded. Fluorine, fluorine and fluorine. Now compared to the nitrogen, fluorine is more electronegative. That's why here it is nitrogen to fluorine and here nitrogen to the fluorine, nitrogen to the fluorine this is. But here compared to this nitrogen, electrons having more electronegativity, that's why that is nitrogen to the electrons. Generally, both are having the same central atom of elements, nitrogen, but attached atoms are bonded atoms are differ. Here hydrogen and here fluorine atoms are there. Here compared to the nitrogen, hydrogen less electronegative and here more electronegative fluorine atoms. Now moment is there, like comparing these two, there is a moment, certain moment is there, but that moment is here electronegativity is more than compared to this. That's why not cancel to each other. There is something value is there. But while comparing this nitrogen fluorine and nitrogen fluorine, resultant dipole moment is cancelled because both are the same nitrogen fluorine, but they are in opposite direction. Equal and opposite in direction. That's why between these two resultant dipole moment is 0. Between these two resultant dipole moment is 0. But between these two not equal to 0. There is something value is there. But your mu is not equal to 0. But comparing these, your dipole moment is less. That's why NH3 has more dipole moment than compared to NF3. Like different examples they will create in examination based on dipole moment and its applications. And also, one of the most important example is stability of cis and transforms. In organic chemistry, in geometrical isomerism, we know geometrical isomerism also called cis-trans isomerism. In this cis-trans isomerism, there exists a carbon-carbon double bond, and attached double bonded carbon atom should contain a 2 different group of atoms like AB. Now, here above the plane or below the plane containing same number of group of atom, either above or below the plane, that is called a cis form, that is the same. Now, if it is different, opposite direction, A and this is B, this is the B and this is A. Now, A is above and below the plane, different, opposite. That's why it is called a transform. Generally, attached group of carbon, double bonded carbon atom containing AB and another carbon atom also containing AB, same electronegativity elements. In such cases, dipole moment of cis form is greater than the dipole moment of trans form. So, cis form dipole moment is greater than compared to trans, because cis means same groups are lie on the same side. Between these two same groups, there is a moment is there, polarity exists. That's why due to the dipole moments, the same charged groups moment takes place. There is a more moment. That's why these are unstable generally. These are more stable based on dipole moments. Because Yeah, A and A or B and B, they are in opposite. One is above, another one is below the plane of the axis. That moment A and A, there is a certain one bond. That bond moment reduces. Net resultant moment reduces. That's why dipole moment is less. For example, now here the C double bond C. This is the Cl and this is the Cl. Now this is the hydrogen and this is the hydrogen. This is a 1, 2 dichloroethene. Formula name is 1, 2 dichloroethene. This is. It is a cis form. Cis 1, 2 dichloroethene because here plane here A and this is B. This also A and this is B. BB or A are on the same side. We can write either like this or like this. Now here the carbon to chlorine there is a movement and carbon to chlorine there is a movement. They are equal and opposite but resultant movement is there. Certain movement is there. That's why yeah, between chlorine there is a movement is there. That's why cis form is more dipole has more dipole moment than compared to the trans form. If it is the same transform in say double bond C, your Cl and your hydrogen atom, your Cl and your hydrogen atom. So here they are in opposite direction. Moment is less. Your chlorine shows say inductive effects, same inductive effect groups. But on simple logic in objective, instead of this, if they'll go like this, your Cl and your hydrogen atom, your hydrogen and your Br if they will give, remember it, different inductive effect groups. In such cases, yeah, the cis dipole moment is less than the dipole moment of the transform. This case is very, very important. When yeah, the attached carbon, double bonded carbon atom, two carbon atoms containing the two same groups. Cis is more means as a dipole moment than compared to trans. Whereas yeah, the attached groups are different at different carbon atoms. In such cases, trans form dipole moment is more than compared to the cis form because yeah, different. This is the minus I effect. This is the minus I effect. But that minus I effect nature is differs. Their value is differ. That's why dipole moment also differs. And also one more important example is generally 1 year asked based on this in JEE examination based on these applications and dipole moment different examples. Generally, your dipole moment in organic chemistry, ortho form dipole moment is greater than compared to the meta form, than compared to the means para form like this. So dipole moment at ortho position, same groups, that is ortho dichlorobenzene, meta dichlorobenzene, para dichlorobenzene. In such cases, at ortho position moment is more. For example, I'll take benzene, simple benzene molecule. This benzene molecule generally has a dipole moment is 0, planar structure. Net resultant dipole moment based on their formula resultant dipole moment mu r is equals to square root of mu1 plus mu1 square mu2 square plus 2 mu1 into mu2 cos theta by using this formula. Its dipole moment is 0. Benzene dipole moment is 0. Planar structure. Symmetrical. Dipole moment is 0. That is a symmetrical molecule. If its dipole moment not equal to 0, something value is there, that is a unsymmetrical molecule. But to this benzene now, your at ortho position, this is the chlorine at ortho position, one more chlorine is there. Between these two groups, there is a certain moment is there. There exists a certain dipole moment. It is called a ortho dichlorobenzene. That ortho dichlorobenzene dipole moment at ortho position is generally greater because between these bond angle is less. less bond angle. Already given, yeah, the dipole moment is inversely proportional to its theta. So bond angle is less, dipole moment is more. Whereas in case of meta position, this is the meta position, like at CL and here CL is there, here angle increases. Angle increase, moment decreases compared to the ortho position. It is a meta dichloro benzene. It is dipole moment at a meta position. This is less than compared to this. Now here at para position, if it contains both the groups are same Cl and here the Cl. Here between these two groups, here carbon to the chlorine and here carbon to chlorine. Both are equal and opposite in direction. Here bond angle is equals to 180 degrees. Minimum, its dipole moment also minimum. That's why here again it is ortho position is greater than compared to the para position. It is para position. Generally, its value is at para position. Its dipole moment is equals to 0. Symmetrical in nature. So only benzene ring is there, planar, symmetrical. But to the benzene, two groups are attached. They are the disubstituents: ortho dichloro, meta dichloro, and para dichloro. Now para dichloro least value almost 0, symmetrical, because its bond angle is 180 degrees. Whereas in this case, you are in para position, instead of two same chlorine, there are two important different groups are present, like chlorine, orthochloro, and it is Br is there. So here two different attached groups are minus I effect and minus I effect. In this case, it is not equal to 0. Something value is there. Even though it is a para position, something value is exists. Moment is there. So based on this, in IIT examination, one year asked here given three important pairs, like one is at para position only CN and here the CN. Now this is the benzene. To the benzene at para position, two OH groups are present, and one more important thio groups is present. Thio group, that is SH and here SH. Now given in IIT examination, like this is A, this is the B, this is the C. Among these three, there are how many compounds shows certain dipole moment? How many molecules are there? Identify it. Option created as A only, B only, C only, or BC only, AB only, or A only, like created options. So based on this, here based on three examples, here it's a dipole moment mu is equals to 0, but these two cases are not equal to 0. Because once we can observe here these groups, here the C triple bond N, CN means that is bonded with the benzene ring. Now this is the C triple bond N. Here benzene, its dipole moment, net resultant dipole moment, benzene value is 0, but there is something is there here. Carbon to nitrogen there is a movement, and here the carbon to nitrogen there is a movement. Here lone pair of electrons are there. Again it is nitrogen to lone pair, like this. Here equal and opposite in direction. This is minus x means it is plus x. Resultant dipole moment must be equal to 0. Whereas in this case, here if we can take this is the benzene, here OH is there and here OH is there. But geometry is not like, because on oxygen atom two lone pairs are there. Here one lone pair and here one lone pair. That's why it shows slightly bent like structure. This is the one lone pair, this is the one lone pair. And also it is a bent like structure here. Two lone pairs are there like this. So here carbon to the oxygen, and again here oxygen to the lone pair of electrons, oxygen to the lone pair. You are exactly cancelled, equal and opposite, but you are not cancelled, because even though you are carbon to oxygen, you are lone pair, oxygen to lone pair, oxygen to lone pair, there is a movement. That's why net dipole moment not equal to 0. Similarly, thio group also, like it is a benzene. Now here S, H, here are the two lone pairs, and here also two lone pairs. Same similarly, here on sulfur atom, two lone pairs are there. That's why there is a movement not equal to 0. That's why among these three, it has 0 dipole moment. B and C ascertain movement. So like in this manner, in examination, objective JEE or NEET or any CET, variety questions based on their application they'll ask. Just based on periodic table and chemical bonding, number of lone pairs, bond pairs, identify what type of compounds, what type of complex compound shows then dipole moment. Okay. After this dipole moments, I'll start one of the most important concepts. So after dipole moment and its applications, another important concept is VB theory, valency bond theory. To explain bond parameters like bond length, bond angle, and bond energies, shape of the molecule, here are four important members introduced one of the most important theory, that is valency bond theory. This is valency bond theory. Valency bond theory. So here, based on this valency bond theory, valency means outermost orbit. So to get a bond, valency number of unpaired electrons are required. So the valency unpaired electrons are participate in a chemical bond to form a covalent bond. Either it is a sigma covalent or pi covalent bond. To explain this, first it was explained by Hitler and London. Hitler and London introduced one of the most important concept. Introduced. Later it was developed by Slater and Powell. Slater and Pauling. Developed by these two people. So main important concept of this valency bond theory is to form a covalent bond or coordinate covalent bond, valency unpaired electrons only participate involved in a chemical bond to get a bond, sigma bond or pi bond. Generally, in valency bond theory, valency atomic orbital overlap. Here, valency atomic orbital means here atomic orbitals your s orbital, p orbital, d orbital, f orbital. Okay. So the shape of s orbital is spherical in shape, like p orbital is dumbbell in shape, d orbital is double dumbbell in shape. This is f orbital is fourfold or the complex. Now sharp it is S, principal P, diffuse, that's why D. It is fourfold, that's why F orbital, F subshells. So to get the covalent bond, these orbitals are overlap. So the extent of overlap is more, bond strength also more. Now the extent of overlap is more for PP overlapping is more than compared to the SP than compared to the SES overlapping. SS overlapping it is. So the PP overlapping, SP overlapping and SS overlapping. Here PP overlapping means p orbital of one atom overlap with the p orbital of another atom. These orbital must contain filled valence electrons that are in same direction before the overlapping. After overlapping, they are in opposite direction. Now here the sp overlapping means one is s orbital and another one is p orbital. This is the overlapping between s and p. Another one is here the ss overlapping. S and s, it is ss overlapping. They are in before overlapping, valence orbitals are in same direction. After overlapping, it forms the opposite in direction. Like against this the SS overlapping like this. In this here one pair is formed. Before overlapping they are in the same direction, they are filled. After overlapping they are in opposite direction. This is the one atom of nucleus, another atom of nucleus, s orbital and s orbital, between there is overlapping, it forms one bond. That bond is called a covalent bond. Now here it forms a like ESP overlapping like this here, ESP. Now here it forms like PP overlapping, PP overlapping. So the extent of overlapping is more for PP than compared to SP than compared to SS overlapping. It is SP overlapping, it is PP overlapping. It is. So based on this, here hydrogen atom and hydrogen atom, here one hydrogen atom electronic configuration is 1s1, 1s1. Here one electron, here one electron. They are off-filled valence electron. Now off-filled valence electrons means s orbital shape is like spherical. They are linearly overlap. This is the internuclear axis. Linearly overlap, it forms a H2 molecule, H bond H, sigma covalent bond is exists. Then here PP overlapping is nothing but the Cl bond Cl here, chlorine chlorine. Here hydrogen chlorine, that is sp overlapping takes place. In that overlapping, that overlapping takes place linearly, or end-to-end overlapping takes place. It forms a sigma covalent bond. Sideways or the lateral overlapping takes place. It forms a pi covalent bond. First example is Cl2 molecule, Cl2. Here the Cl plus Cl, it gives a Cl2 molecule. 17 atomic number, electronic configuration, neon 3s2 and 3p5. Here two are paired, remaining among 5, 2 pair and 1 is unpaired. It is 3s, 3px, 3py, 3pz it is. Or maybe take 3pz, 3py and 3px. Anyone. directions, that's all. X, Y axis, Z axis. Now your Z is the internuclear axis. Imagine as Z axis is considered as internuclear axis. Internuclear axis. In this internuclear axis, according to VB theory, yeah, this is the internuclear axis that is contain one off-filled unpaired electron. P orbital shape is dumbbell. Now this is the P subshell contain 5 electrons. Yeah, S subshell contains 2 electrons. Total valence electrons are 7. Among 7, 1 electron is unpaired. According to VB theory, valency unpaired electrons are participate in a chemical bonding for overlapping purpose. That's why in P subshell, PZ orbital, this is 1 chlorine atom, 3PZ contain 1 electron of chlorine. Another chlorine also same here 3PZ1 is there, that is here 1. Now nucleus of P orbital, one line is passed through the nucleus, that is called a internuclear axis. This also a internuclear axis. One 3PZ or any PZ orbital of off-filled valence electron linearly overlap with the another chlorine atom 3PZ or PZ orbital linearly combines. It forms a one sigma covalent bond. That is called a end-to-end overlapping. Now this is end-to-end overlapping. Here it forms an electron pair. Here PZ and PZ. Now it is a sigma covalent bond, that is for chlorine 3PZ and 3PZ. For some other atoms maybe 4PZ, 4PZ. Like here the Cl bond, the Cl exists when sigma covalent bond is formed. After formation of sigma covalent bond only, other multiple bonds, pi bonds are formed. In 2 bonds, one is compulsory sigma bond, remaining bonds are the pi bonds, multiple bonds. Like pi bonds, multiple bonds are formed by sideways or lateral overlapping, not end-to-end overlapping. I'll give an example, best example to you, that is oxygen molecule. You are an oxygen molecule, O2 molecule. Your O plus O gives O2 molecule. This is atomic number 8, electronic configuration 1s2, 2s2, 2p4 it is. Outermost orbit. Here it is 2 electrons and here 1, 2, 3 like 4 electrons. These two are paired, but these two are unpaired. It is 2s, it is 2px, 2py and 2pz. In 2py and 2pz, each one electron is unpaired. Same similarly in another oxygen atom also same. That's why this is the oxygen atom. This is the 2pz and 2pz. And this is the 2py. For understanding purpose, these are the shaded line. These are this is 2py 1 electron, this is the 2pz 1 electron. This is considered as a internuclear axis. Another oxygen atom same, this is another oxygen atom. Now this is the 2pz it is, and it is 2py oxygen atom, 2py. Here 1 electron is there. Now, initially, without forming this internuclear axis 2pz and 2pz overlapping, end-to-end overlapping, sideways overlapping cannot take place. That's why in this oxygen molecule, 2px is completely paired. That's why no need to show here orbital completely filled. Already paired it is. In its outermost orbit, valence shell 2 are the unpaired. That's why 2py and 2pz orbitals only participate in overlapping. So one oxygen atom of 2pz, another oxygen atom of 2pz. These two are same symmetry, Z only. That is a positive sign. They are in a phase. Overlapping is strong. If it is 2pz and 2px is there, that is not in the same phase. They are in opposite phases. They are negative phase. Out of the phase, overlapping will get it. I'll give the combination, phases combination. So are the 2pz, 2pz only, but 2pz cannot overlap with the 2px or 2py because axis also may be similar. Now linearly overlap, it forms a sigma covalent bond. That is called a end-to-end overlapping. After formation of oxygen and oxygen, end-to-end overlapping, either electrons around the nucleus of oxygen continuously revolves either above the plane or below the plane, sideways overlaps. Here the sideways overlapping takes place or lateral overlapping takes place. It forms a pi covalent bond. So here the sigma and pi covalent bond. This pi covalent bond is formed by only p orbital or the d orbital. Yeah, pi bond not s orbital is not formed. To form a pi bond, compulsory p and d orbitals only possible. They are involved sideways, it forms pi bonds. Like p pi and p pi bonds, both are the p orbitals. If they are the different d orbital, that is p pi and d pi bonds are present. In second year, 15th group elements, some bonds are there. P pi or the p pi, d pi, like bonds are there. Now here these pi bonds are always formed after formation of sigma covalent bond. So here the pi bonds are generally present along with sigma bonds. That's why sigma bonds are the stronger than compared to pi bonds. Pi bonds are the weaker. Number of multiple bonds increases, bond length what happens? Decreases. Like chlorine, there is a sigma bond. Oxygen, double bond. Nitrogen, triple bond. So number of bonds increase, what happens? Bond length decreases. Bond length decreases, bond enthalpy increases. That's why VB theory clearly explains the shape of the molecule, bond parameters like a bond length, a bond angle, and bond energies. Clear? Sigma bond and pi bond. Its strength, the differences between sigma and pi bond. Yeah, the sigma bond always formed end to end. Pi bonds are formed by sideways. After formation of a sigma covalent bond, pi covalent bonds are formed along with the sigma pi covalent bonds. But sigma bonds are present alone. First, sigma covalent bonds only formed. So the pi bonds are formed by p and d orbitals, not by s orbitals. So maybe in examination based on this, here this is the p orbital and this is the p orbital, one atom and another atom. They are positive and positive, yeah, negative and negative. While overlapping these two, these loops sign is the same, positive, positive. Or maybe it is negative, negative, it is a positive or positive, same sign. We'll get the one important overlap. That overlap is positive phase. They are in phase, positive overlapping. If it is different signs are the loops, like it is positive and it is negative. It is negative and it is positive. While overlapping these two atomic orbitals, they are not in the same phase. They are out of the phase. That combination is called generally negative phase. Negative phase are out of the phase. Out of the phase. Some are zero phases are there. Zero overlappings are there. Like this is even p orbital, positive and negative nucleus. It is overlap with the s orbital like this. S orbital. This is called a zero overlapping. Zero overlap it is. So are the some are positive phases are there, some are negative phases are there. Positive phases means sign loops Loop's sign must be same, positive positive or negative negative. Positive means electron overlapping either clockwise or anti-clockwise direction, or negative negative or positive positive, must be same sign. Loop's sign will get a same phase overlap. While overlapping these atomic orbitals, there are some attractive and repulsive forces are there. For example, in this attractive and repulsive forces, your A atom combines with B atom, it gives AB molecule, or your A2, B2, it gives 2AB. Between AB is there, so between A and A there is a bond, between B and B there is a bond is there. Then here we'll get A into B, like one molecule is formed. These are the old bonds, strong bond. It is also a old bond. Now it is a new bond is formed. So these old bonds are ready to break to form a new covalent bond. Okay. Now while reacting these two, between these two atoms, your Na is nothing but a nucleus of A. A is nothing but electron of A atom. This is the nucleus of B atom and electron of B atom while overlapping. This is an atom of element. Imagine as an atom of element nucleus, that nucleus atom A, that's why this is a Na, and here electron is present, that is Ea. Now here this is another atom of element nucleus, that is Nb, electron is Eb. These two are while combining, atom A and atom B, there are some attractive forces are there. Attractive forces. So the attractive forces means that attractive forces is generally exist between nucleus of atom A and electron of atom A. Here exist effective attractive forces, and also here the nucleus of B and electron of B attractive forces exist, or maybe your nucleus of A and nucleus of electron of B, or nucleus of B and electron of A attractive forces exist. But there are some repulsive forces are there. Repulsive forces means your electron of A and electron of A repulsion, or electron of B and electron of B, or electron of A and electron of B atom repulsions takes place, as well as nucleus of A and nucleus of B also repulsions takes place, because nucleus charge is positive, repulsions takes place. Your electron charge minus repulsions takes place, repulsive forces. But here the nucleus is positive, electron is negative, attractive forces exist. Na plus nucleus, it is electron charge is negative. Here there are some attractive forces. Same here, the nucleus and electron, there exist attractive forces. While overlapping between two atom of elements, there are some attractive and repulsive forces. Maybe based on this, they'll create an important question. In what phase, in what way, attractive and repulsive forces takes place. Okay. So tomorrow we'll discuss about, after this VB theory, tomorrow we'll discuss about valence shell electron pair repulsion theory to explain now shape of the molecule on the basis of a lone pair concept. So lone pairs and bond pairs concepts. Okay. So better you read all synopsis of VB theory and Vesper theory along with VB and Vesper theory. I'll start tomorrow hybridization. After hybridization, there is one simple concept, that is MOT. After that MOT, we'll start some previous year questions. Okay. Take care.